Well, thanks for attending this workshop centered on variational quantum circuit or quantum neural network. In this session, we are going to review. Let me a moment. In this session, we continue analyzing this kind of model, adding more information about the state of the art and the problems and the challenges about this model. We'll make a brief introduction on the main concept that we are going to see in this presentation, starting with an abstract vision and going into the details in an incremental way. So there are the topics that we are going to talk about. Firstly, we talk about the current state of the art on quantum machine learning, followed by the methodology, architecture, and encoding strategies that we can use in this kind of models. Of course, its challenge and its potential, and ends with an implementation for iris classification problem using penny lane, PyTorch, and also the data reloading technique. So let's start. In the literature, we can find several approaches for supervised learning. For example, the use of quantum neural network for classification and regression problems. We can also find the quantum version for Q-iris network and also for the support vector machines. Related to unsupervised learning, we can also find the quantum version for the clustering. And finally, related to reinforcement learning, this area has received less attention than the others, but because it's in early stage, but mainly we can find two approaches for the implementation of the quantum agents, such as Grover iteration and the use of quantum neural network. Any question at this point? Variational quantum circuit, also known as parametrizer or parameterizer quantum circuit and quantum neural network, due to the similarities in the trainable mechanisms, because in both cases, in the classical neural network and the quantum neural network, we have to optimize the parameter, the trainable parameter, or learnable parameter of the network in the direction of the minimization, the objective function, using gradient-free or gradient method. If we decide to solve this problem using gradient-free method, we can select evolutionary algorithms, for example, genetic or PCO, among others. But in case we decide other algorithms, gradient-free, for example, we can select natural gradients. But in case that we want to work using gradient method, we have to use classical optimizer, for example, Adam, RINSPRO, ISGD, among others. So in general, this model, similarly as the classical code part, the classical neural network, can approximate any continual function, any objective function, for example, the cost function, or in case that we are working on reinforcement learning, the optimal policy agent. The step to follow in working with quantum machine learning is very similar to the classical machine learning, starting with a preprocessing stage in which we prepare the data. The data is still in this step in classical format, preparing, applying several transformations, for example, standardization, normalization, or one-hot encoding. This step is executed in the classical part in CPU, and after that, the data goes to the next layer, encoding layer, or also named feature map or embedding layers. This layer is in the quantum hardware QPU, and the objective of this layer is map the the classical data into quantum state, commonly formed using rotational gates, for example, RRI or RS, applying into the classical data. This is the equivalent to the input layer in the classical neural network. So the data that is already done to be in quantum state goes through to the next layers. The next layer is the variational layer or the unsharp layer. In this layer, the objective of this layer is the execution of the quantum algorithm, commonly formed with a rotational and entanglement gate. This layer is equivalent to the hidden layer in the classical ones. And we can find in this layer the learning parameter, the learnable or trainable parameter, the weights of this network. And the next step is the measurement process. We can obtain the observables of this quantum system, do the measure in the computational basis, or if we want to do, get the state vector of this quantum system. After that, we can post-process this output in the classical hardware, for example, applying to this output transformational function, for example, softmax or other probabilistic distribution function, with the objective to getting the expected output. So we have to calculate the cost function or policy in case of reinforcement learning, and applying the optimizing of the parameters using gradient-free or gradient method, of course. This is an iterative process very similar at the classical neural network, but here the iteration happens between the classical hardware and the quantum hardware. This is the difference. We can get more expressive circuits, I mean repeating several times the variational layers. With this technique, we can obtain accurate model, more expressive, because can approximate in a better way this objective function. But we can also find in the literature more complex architecture, for example, including trainable or learnable parameter also in the encoding layers. This is the technique named data reloading and data rescaling. The objective of this technique is get more expressive circuit that can approximate in a better way the entry data. I mean, suppose that you have a sine function, so you just have a very simple function, very simple way. So with this way, you can express very few data. But imagine that you repeat again and again this function and also adding more function, for example, cosine. You get more data, so you can express more data with this new function. This is a Fourier series. So you have to ensure, or we have to ensure, doing this technique, that all the entry data are included in the period of this function. So doing this technique, also as we mentioned before, repeating the unsharp layer, we can get more expressive models. So for that, accurate model and can approximate in a better way the objective function. But there is an inflection point. I mean, there is a point in where you add more layer, more qubit, or more entanglement gates that there is no an improvement in the learning. Instead of that, the learning becomes stuck. There is no learning. So this is the phenomenon named Barren Plateau. This phenomenon is very similar at the classical neural network named vanishing gradient, but is more present in this kind of models. So to avoid it, we can practice several techniques, for example, reducing the number of qubits, the number of layers, the number of entanglement gates, and also using higher learning rates. In case that this is not enough to solve the problem, we can decide to use other methods, for example, gradient field methods. It's very important, so for build very accurate models, the selection of the ansat architecture, the encoding strategy, the selection of the observable, and also using very simple but very expressive circuits. Very simple in the, I mean, using reduced number of qubits and also the reduced number of layers. Any question at this point? Okay, let's continue. If everything is not clear, please ask whatever you need.
Thank you.
Thank you. So, relating to the encoding strategies, we can find several methods. The most important are the following. For example, basic encoding is the most easier, but have the problem of the efficiency because you need as much qubits as the higher value on your data set. I mean, this not depends, the number of qubits not depends of the number of features, but depends of the values of your data set. So the traceability is very easy because you have only to pass the data, the value of the data to a binary, so you get directly the quantum states. Other method very often to use and is more efficient is the amplitude encoding. With this method, you just need logarithm of n, where n is the number of features of your data set, or in the case of reinforcement learning, your environment variables. So you have to do a first step, normalization, to ensuring that the longer will be 1, and after that, the quantum state is the following, no? That you can see in the slide. So it's very efficient, this method, but the traceability is getting worse than the before one. Other strategies is the angle embedding or tensor product embedding. Very often in the quantum algorithm that consists only applying a rotation gate to classic data. There is other variant of this strategy named dense angle encoding that take advantage of the relative phase and applying after the rotation gate a phase shift gate. This way of encoding is more efficient than the previous one because they just need a half of n qubits, where n is the number of features. So at this point, the most efficient method for encoding is the amplitude encoding and dense angle encoding because it requires lower number of qubits than the others. So the most often architecture that we can find to build quantum neural network and for solving the dimensionality problem. I mean, imagine that you are working with a data set with 20 features, but of course we feel more comfortable using a lower number of qubits. So instead of use 20 qubits, we try to reduce to 10 qubits or lower. Because if you, of course, obviously we don't have as many qubits as we want, and also we have to keep in mind the computational cost working with simulator and emulating this quantum operation with classical hardware. So it's very it's very efficient to use. The recommendation is use a circuit more simpler with a number of reduced qubits. With a reduced number of qubits. So to do that, as you remember, I explained it before, we can use the most efficient strategies to encoding in order to reduce this number of qubits. So In this case, the architecture will be formed for the following layer: a pre-processing data, executing the classical part, as I mentioned before, an encoding layers that try to do an efficient encoding strategy. After that, the variational layer, dancer layer, the measurement, and a post-processing done again in the classical part. So this is the architecture of the quantum neural network in a more pure way of development, because not include any additional layer in any classical layer in Python or in TensorFlow that we are going to see in the next slide. Any question about this topology or this architecture? Okay. So the next approach includes a classical layer that could be in Python or in TensorFlow to do this linear transformation in order to reduce the dimensionality of the problem. For example, in the same problem, we are working with 20 features and we feel more comfortable using 10 qubits instead of 20 qubits. So we can apply a linear layer in Python or in TensorFlow that can reduce the number of 20 qubits to 20 features to 10 features that can be managed in a better way by our quantum circuits that only use 20 qubits. So this is the schema. As you can see, it's very useful. You can see in Qiskit, in PennyLane, and other stack, other software, other libraries. So the process is very similar to the previous one, only between the pre-processing and the circuit, you added a new layer that includes this linear transformation, a linear layer. So the problem of this model is not as quantum as the previous one because included a classical layer between the quantum circuits. So you have an hybridization of this model. It's a hybridization model, hybridization approach. So at this point, we know the challenge, or we have an intuition about the challenges and the potential about the models. Regarding to the challenges, as we mentioned before, we have the problem of the dimensionality. So this problem already exists in the classical machine learning, but we have to focus on this problem because it's very important in order to avoid the barren plateaus, also reduce the computational cost, and also reduce the number of qubits because we don't have as many qubits as we want, no? So this problem is very important to keep in mind when we are working in more complex, with more complex data set, with many features, or with environments with a lot of problems in the real world. Other problem is the barren plateaus, is a weakness of this method. The scientific community is very focused on this problem because it's a weakness and have a very high interest in this area. We can solve, we have several strategies to solve. Remember, reducing the number of layers, number could be higher learning rate, or in case not the solution, change to other method, no? Gradient-free method. In addition, in classical machine learning, we have a standard architecture and guideline to follow for solving different problems, different use cases. I mean, we have to solve a computer vision problem. We have a specific convolutional neural network, a specific topology to apply in this kind of problem. If we have to solve a binary classification, we have a specific error function, a specific topology in multi-class or whatever we need, no? But this is not the case for the quantum machine learning. We don't have any guideline or any standard architecture to follow, depending of the problem that we have to solve. The potential. So these models are very compacted in the sense that the number of parameters required are lower than the classical ones. So it's more efficient in this sense. Can't detect patterns hidden that the classical ones cannot detect because are very well solving complicated relationship or detecting more than solving detecting complicate or complex relationship between the data. So we can obtain better accurate model, have a higher potential in this sense. In addition, they take the advantage of the parallelization of the quantum computing. But in summary, this model, the potential of this model is under research. So let's go. At this point, we are going to do an implementation using penny lane and PyTorch and also data rerouting technique in the iris classification problem. So for that, we starting preparing the model to do a benchmarking, firstly doing in a classical, using classical neural network, and after that, the quantum neural network. So starting with a classical neural network, we use PyTorch. So the first step, as you can see, is loading the data set with using scikit-learn library. As you can see, we have three classes, setosa, versicolor, and Virginica. And we have 4 features, sepal length, sepal width, petal length, and petal width. We pre-process this data using the standard scaler and splitting the data set in train and test data and test set. To avoid the distraction, we prepare this example without doing any IDA or applying CAFOR or small other recommendation, highly recommended using quantum machine learning. No? In order to be the most simple example, we are going to do only the necessary step to understand the model. So after they prepare the data set, we define the model in PyTorch, which just need an input layer formed by the 4 features. As you remember, the 4 features that we have in the data set. A hidden layer formed by 50 neurons in the hidden layer, and 3 neurons in the output layer that correspond to the 3 classes. Respect to the forward, we have multi-class classification. We are going to use softmax function. So this is the summary of the topology of the model. After that, we are going to do the training using 100 epochs. So after the epoch, we measure in the test data set and get the following learning curve. As you can see, the curve looks good. Get the accuracy nearly the 80 epoch. So have a very good learning progression. The same for the lost. So it's have a very good metric, no? So in this point, we are going to develop the quantum neural network. So as you can see, we import the penny lane library. After that, we define the quantum circuit that as you remember, we have to implement the embedding or the encoding layers or the feature map layers. In this case, we decide to use a very simple encoding layer because we have a very few number of features. So we just only apply a rotation gate in the classical data. We obtain the input embedding. After that, we have to develop to build the ansat of the variational layers that in this case is composed by rotation and entanglement gate. We can decide, it's very experimental, the selection of this gate, because you have to, you can choose this gate or rotation on I-axis or CZ as entanglement gate, whatever you need, because this depends on the problem and the similar way as the classical machine learning, because depend the solution, the number of neurons, the number of layers, the learning rate, or the pre-processing of the data, depend of the data and also the problem. In this case, it's very similar. The use of one rotation or one entanglement gate from others instead of others depends on the problem, the nature of the problem and the nature of your data. So after the answer layer, we have, if you remember, the step of measurement. In this case, we select the selection of measure on the computational basis and forget the observables. So this model is embedded into a touch layers that Penny Lane let us to do that. So we have the model to be trainable using gradient method in this case. Any question at this point related to the topology or whatever?
Yes, one question. Hello, Eva. I'm Robert. Do we use 1 qubit per feature or like four qubits, right? Or
Yes,
less?
exactly.
Okay.
Four qubits in a total, one per feature. Yeah, in a simple way.
Okay.
If I decide to imagine if we have 20 features, we can apply other morphism encoding strategies, amplitude embedding or dense angle encoding.
Okay. Thank you.
Thank you. As you can see, we have two parameters, learning parameter in the ansat layer. As you can see, in parentheses, wait, two number of parameters, one for first rotation gate and the second for the second rotation gate. So this is the class that will contain the circuits, the quantum layers, and only include, if you remember, a pre-processing and post-processing step that have to be executed in the classical part, in the classical hardware. The forward, as you can see, contain the pre-processing after to invocate the model and post-processing after the invocated model. So pre-processing before, invocate the model, and after apply a post-processing of this output. Any question in this part? Okay. So as pre-processing, in this case, this is also very experimental. So in this case, we tested with using MPP divided by 2 because my intuition said it's a multi-class problem, so we can manage more than 2 variables if I rotate between 0 and NumPP. So we can test with NumPP divide 2, but there is other case that you have to divide with 4, 8, or whatever. In case, imagine we have a binary classification, I tested this problem that the mode pre-processing is only use NumPP in the escalation of the entry data. So, but this is very experimental. Any question about this, the pre-processing, and when you use any escalating value on other? For example, suppose that you have a tangential function that have values between -1, 0, and +1. So you have 3 values. So instead of using NumPP, you have to use NumPP divide 2 because you have between values between -1 and +1. So, but it's the very intuition. You have to test this intuition with the experimental result. No? As post-processing, as you can see, we only apply the softmax because we are working with a multi-class problem. Is I working in binary problem as sigmoid, of course. So here we define the hyperparameters. We define the pre-processing function, post-processing, the number of layers. As you can see in the topology later, we repeat the answer layer 15 times. The loss function, the learning rate, as you can see, the learning rate in quantum neural network is higher than the classical one that usually use 0.0001, but in this case, higher values. To avoid the Barren plateau, we use 100 epochs, and this is the circuit, embedding the circuits in the class, using Adam as classical optimizers. This is the configuration of the circuits. As you can see, we have the encoding layer with rotation gate and repeat 15 times the answer layer with the entanglement, the rotation with entanglement, and zeta is the observables. So this is the topology of the circuit. This is the training process, is the same way as the classical ones. And this is the result. As you can see, the learning curve have a better accuracy, a better behavior than the classical ones, achieve the convergence sooner than the classical one, and the behavior are very stable. So the variance, there is no variance, only at the beginning. So it's look better than the classical ones. In this case, now we are doing the same, but applying data reloading technique. It's very similar, but we have, remember that we have to include other learning parameters in the encoding layers. So we have to use different optimizer, classical optimizer in the answer layer and in the encoding layer, or the same, wherever you need with different learning rate or whatever. In this case, we use different, even have the same values, but I added here to do in necessary case, no? Change the values. So this is the circuit, this is the container of this circuit, and this is the multi-optimizer. This is the weight or the learnable parameter for the encoding layers, and this is for the answer layers, the weight. In this case, we're also using 4 qubits. This is the composition of the neural network. As you can see, in the case of data reloading, we repeat several times the encoding layers. As you can see, we have here the learning parameters. In case that we decide no use, we don't have any learning parameters. And for the answer, the same, the weight for these layers. And this is a case for it is exactly the same than the before use case without using data reloading and data rescaling. The touch layers that include embed this circuit. And this is the topology of the circuit. As you can see, we repeat also the rotation Ri in each layer several times until 50 times. And finally, we get the observables. Any question at this point? Okay. This is the multi-optimizer, how the class that embed the optimizer to be used in different ways, one per ansat layer and the other one for the encoding layer. So if you practice using different learning rate, as prop or is GD instead of Adam or Adam Max or whatever. So this is the training, it's the same. And this is the result. As you can see, the model in this case not get improved learning than the other. We have more unstable, have a good values also, but is more unstable than the previous one. So in this case, the data reloading no achieve better accuracy, no, for this model. But in other case, of course, yes, so it's the same as classical ones. In one case, a solution, one approach runs okay. In other case, not, because it's very depending of the problem. So a part of we find this model get accurate, get better convergence than the classical one. We have other advantages like the number of parameters. I included here the calculation of the number of parameters in the classical neural network. In this case, we have 50 neural network in the hidden layers, 4 in the entry, in the input layers. This is the 5 for the weight, and this is for the BX. So in total, we have 500 parameters. In the case of, this is clear, this formula? Do you imagine to calculation the connection between the layers? For example, the input layer connect with the hidden layer. So we have, if we have 4 neurons, we have to multiply with the hidden neural network. So, sorry, with the neuron in the hidden layer. So we have to multiply 4 the input layer with the number of neurons in the hidden layer. And here is with the numbers of the weights, and the same for the VX in the output layers.
Sorry, I have a question about this data re-uploading neural network. So you mean here for every layer you re-input your data every layer, right?
In data reloading, yes. You input the data in here. Here is the calculation for data reloading. Yes.
Yeah. Then do you consider entanglement here in between different qubits?
Sorry, I don't
I mean, I'm not sure how many qubits do you use here, but if you use more than 2 qubits, then do you consider any entanglement here?
Yes, but I need exactly the same number of qubits for qubits in case of data reloading or not data reloading. The only difference is repeat the layer several times using a parameters, other learning parameters in the encoding layers. Because the model learn again and again in each iteration how to express in a better way the same tree data. But the number of qubits remain exactly the same.
All right, but you consider more than 1 qubit, right?
Yes, you can consider more qubits, but in this case, it's not necessary to add more qubits, because with 4 qubits, you can represent in a very, very good way the 4 features of this data set.
Okay, because yeah. Okay, I see. Yeah, thank you.
In case that you for example, suppose I'm working with 20 features, we can reduce to 10 qubits using dense angle encoding, for example, or logarithm of 20 qubits in case that you need that you are going to use amplitude encoding. But this is not, but if you are using data reloading, you are not going to reduce or increasing the number of qubits. It's exactly the same. The only that you are repeating is the circuit, in order to prepare to build a Fourier series that can represent in a better way the objective function, the cost function or whatever. But
you benchmark different architectures with the same resources. Okay.
Yes, yes. There are two different architectures for the quantum neural network. Quantum neural network in a basic schema, which only have learning parameter in the ansatz layers, is the more easier architecture, the more simple. And other technique that use data reloading and data rescaling schema in order to get more expressive circuit, can approximate or get accurate model. With the difference of we are adding other learning parameter, other weight, also in the encoding layers, not only in the ansatz layers, and also repeat the encoding layers several times, not only the ansatz layers. Because in the first approach, we repeat several times the ansatz layer, but in the second approach, using data reloading, you can repeat ansatz and encoding layers. Emulating in the data reloading, you are trying emulating the functionality of the classical neural network in the sense that you repeat the entry neural network to each neuron in the hidden layer. But due to the non-clonation theorem in quantum computing, you are not able to copy these neurons, this circuit to the next layer. So the mechanism to do that is repeat this layer, the entry layers, the embedding layers, several times. This is the way that you emulate in a better way the functionality of the classical neural network. I hope I answered your question, no complicate more. So this in summary, we have two techniques to solve this problem. The first one, the quantum neural network, without using data reloading, forget that. It's very simple. You only need encoding layer that prepare the data, an ansatz layer that has to be repeated several times, executing the step of the algorithm. And that's all. That's all. So you only have one learning parameter in this layer. This is the more simple model. Other complex model is the use of data reloading and rescaling technique, in which we added other learning parameters in the encoding layer, with the objective to the model learns in each epoch how to express in a better way the entry data. I mean, in a better way, the Fourier series that represent the data. So you have two types of parameters in the learning, in the answer, in the encoding layer, and also in the ansatz layer. And repeat for that the ansatz layer several times, 50 layers, for example, and also repeat 50 times the encoding layers. I put again the topology of the circuit in order to clarify it. This is the topology of the first approach without the use of data reloading. You only have an encoding layer composed by rotation gate, this one, and after that, two rotation gate and entanglement gate. These are repeat 15 times the number of layers that we defined in this model. So we only repeat the answered layers, but only execute one time the encoding layers. So in case of data reloading technique, as we can see, we see the encoding layer also in each layers. We repeat 15 times the encoding and the unsat layers, not only the unsat layers. Is more clear? Or do you still have the doubt?
One question, Eva.
Yeah.
As we repeat these Y rotation gates through the circuit, the numbers, the parameters shouldn't be the same because the input is the same. I mean, in this first it's like 0.08 and in the second layer is 0.23. I don't know, they should be the same or?
Yeah, this is an example to draw the circuit. I'm going to show you the code. Let me because I initialize the weight to draw the circuit with values, but it's not the screenshot of the neural network models. Yeah, it's an example to initialization. It could be a screenshot of the models of the neural network, but it's not exactly the real, it's in a sample only.
Okay.
So in each epoch, the model applies different weight because applying gradient descent is very similar as the classical one.
Mm-hmm.
Calculate the gradient and apply optimizer, background propagation, the error around the weight, updating this weight.
So in the real case, for each sample, this circuit would have the same numbers in the rotation, Y rotation, right?
Yes, with other values or with these values, but this is the values of the, the weights are in the encoding layers in this rotation gate or I, and also in res X, in res zeta. In this case, we have in the encoding I, we have the weight of the encoding layers and other parameters, 2 more in the unsat layers, because in this case we use only, in the encoding layer, we use only one parameter because we have only one rotation gate, and in the unsat layer we use 2 weights, 2 parameters because we use two rotation gates. If we need other rotation gate or other gate operation, we added other parameter. So in summary, we have one parameter for encoding and is the other rotation gate. Finally, we obtain 3 weights in the unsat layer, 4 weights in total.
Vale. Okay, thank you.
Voy a switchar un momento al español. O sea, tú lo que tendrías es en la primera capa de encoding, en la rotación de I, un weight, un parámetro. En la parte de ansat tenemos 2 weights, 2 parámetros, uno que sería para la rotación en X y otro para la rotación en Z. Si añado otra puerta, imagínate otra RI, pues tendría 3 weights en esa capa y un weight en la primera. Eso sería. Y esto es un screenshot que he puesto con la inicialización de los pesos, ¿no? Para poderlo dibujar. Pero esto podría ser, si capturásemos, diéramos una foto a la red neuronal en un momento del aprendizaje, ¿no? Podría ser encajar perfectamente. Esos serían los valores de los weights.
Vale, es que creía que en la rotación y metíamos directamente el valor de input.
No,
un weight.
Bueno, en la primera sí, en la rotación primera sí. Lo que pasa, eso si no usa data reloading, ¿vale? Sería ahí. Si no usa data reloading, sí, porque lo que va a hacer es aplicar al dato clásico, lo multiplicas por NumPy o lo que tú consideres oportuno y ya con eso obtienes el quantum state, ¿vale? Entonces, ahí no hay peso, ahí no hay parámetro, ahí no está usando. Pero si decido usar data reloading y data rescaling, en el cual el modelo aprende en cada iteración cómo aproximar mejor a esos datos de entrada, ¿no?, que estoy teniendo, ahí estoy utilizando parámetros de entrada, que te los voy a enseñar, que son estos de aquí, los WI. Porque voy a usar parámetros entrenables en el ANSAT, que es el modelo básico y estándar, y también en la parte de encoding, que sería esta. A ver si lo veamos. Estamos. Este es el normal. A ver que te enseñe el layer, que pone layers. Aquí está, layers. ¿Ves que aquí hay dos parámetros? Este que sería el weight y el weight in. Weight in, no sé si ves en la pantalla,
Sí.
pone weight initialization, ¿no? Weight in es el de la capa de encoding, cuando voy a usar data rescaling y data reloading, ¿vale? Si no, no hace falta. Y el primero es el que antes tenía, que es el de la capa ANSAT. Entonces, ves aquí que en vez de multiplicar por NumPP partido por 2, lo que estoy haciendo es multiplicando por los pesos que voy generando en cada aprendizaje. Que aquí sí va cambiando. Aquí ya no multiplica por NumPP. Aquí va multiplicando por el valor que va aprendiendo.
Ah, jope, claro.
Al igual
ahora
que sea aquí. Igual que, ¿veis que aquí pone weight en el ANSAT? Y aquí pone weight in, WI.
Vale. Okay, sorry for the Spanish.
Ah, no,
Vale.
no worries, no worries. So, in summary, we have to, in case of we decide to use data reloading technique, we add two weights, one for encoding layer. As you can see, in this case, we are not multiplying by NumPP, we are multiplying by the weight that we are learning in each step at a similar way as the ANSAT. In ANSAT, we use the weight for this layer, learning in each epoch in each iteration. So we have both parameters, one for the encoding layers and other parameters that form composed by two values, one for this rotation gate and other one for the second rotation gate. In case that we need to add other rotation gate, we added other parameter in these layers, in the ANSAT layers. Okay, so instead of use two, I use 3 parameters in these layers. You can see this in the parent chase. Weight is the weight of the, can you see the parent chase in the, before the Q node? Here is more clear, in my opinion, because you have the number of parameters in the ANSAT layer, 2, because I have 2 rotation gates, and in the case of the encoding layer, because we are using just a parameter in this layer, we only want 2 parameters. Is added other rotation gate, this move from 1 to 2. So this is the mainly difference. No? Any doubt? Okay, anyway, I passed the notebook, but you can test it and toy with them. And in any case that you continue keeping this doubt, please contact me without any problem, okay? So, talking is, in summary, the number of parameters in the classical neural network are higher than the quantum neural networks because in the first formula, we can see that in the case of classical neural network, we use 4 neurons for the input layer, 15 neurons in the hidden layer. So 3 neurons in the output layer have to be multiplied with the number of neurons in the hidden layer for the calculation of weight. And also don't forget the the biases multiplying by 3 also because we have weights and biases. So in total, we have 500 parameters. In the case of quantum neural network, this is the formula. And we have to without using the data reloading, so we have no parameters in the encoding layers because only apply a rotation of the classical data multiplied by num-pp or num-pp divided 2, so we don't need any parameters. Adding the number of layers, 15 layers, the number of parameters, as you remember, we only have 2 rotation gates, so 2 parameters, and 4 qubits. So in total, we have 120 parameters. And in the case of data reloading, we have parameter also in the encoding layers. So we have to multiply the number of layers 15 with the number of parameters 1 and the number of qubits 4, adding exactly the same. So in total, we have exactly the same as the previous formula without using data reloading. So because in this part, anything changed. So in total, we have 180 parameters. So we can check the number of parameters in the quantum neural network are lower than the classical ones. So in this sense, these networks, this model are more efficient and more compacted. So it's very useful in case that we have to deploy this model in a little hardware. For example, imagine a fire detection or whatever. So it's very useful to keep in mind. Conclusion about this use case. These models are more compact and more efficient, as we explained before. We need less epochs to converge, but this only this is for this use case. Of course, in other use case, a more complex case, we have other complications that we mentioned before. For example, the Barren-Plateau, the dimensionality problem, so that could complicate the solution or the convergence of these models, no? Also, we can keep in mind the computational resources because the emulate this operation using simulator are very hard. Take hours and hours. In this case, the data set is very simple. But imagine in case fraud data set or other with thousands of register, so you have to manage many information in the memory, so that consumes a lot of resources. So this is the bibliography used in this presentation. And that's all. Relating to the advantages of this model, it's very difficult, in my experience, of course, it's very difficult to get a better, accurate model in classification or regression model because this model in classical machine learning are very efficient, no? We have guidelines, standard topologies, and so on. But in my experience, it's more easy to find an advantage on an advantage in the sense of a curated model that converges that sooner than the classical one that need less epochs to convergency than the others. So in reinforcement learning, using this kind of model, due to the combination, you have not all the information and you have to test several paths, execution paths, because a stochastic environment runs very well in this environment. This is from my experience. No? And that's all my explanation. Whatever you need is you need to explain with more detail or other subject or other some of these topics, please let me know.